let's briefly describe Kepler's 3 laws of motion. And what's amazing about Kepler is he did it all empirically. He just looked at data taken by Tycho Brahe long before telescopes, long before we really had advanced mathematical techniques. There's no calculus or anything. But he figured it out, and it took him 20 years. But it was one of the great intellectual achievements of all time. And so what he found is this: planets circle the sun with an ellipse. Now I'm going to draw an exaggerated ellipse, something like that. And these are the foci of the ellipse. One focus here, one focus here. So we call them foci. Actually, it kind of looks like the Big Hero 6, doesn't it? See it? Okay. No. Now, what's right here? The sun. What's over here? Nothing. There is nothing at the other foci, or focus, the second focus. Nothing's there. It's empty space. The sun is not in the middle. And this will be on the AP test, and so they could give you a diagram, and they'll give you different pictures of like what describes the where is the sun located, and they'll put the sun here, or they might put it in the very middle. It's not in the middle of the ellipse. It's at one of the foci. So that's the first law. The sun is at the focus of an ellipse. Is the ellipse 1L, 2Ls? I can't remember.
2Ls.
Hit him. Okay. Okay, thank you. Okay, the sun is at the focus of an ellipse. So that the planet is moving in an ellipse. Now, by the way, there are objects that move in an ellipse this looks like that, like comets. Go through the solar system like that. But planets, they do move in an ellipse, but it's the two foci of the ellipse are very, very close together. They're almost, in fact, if you were to look at a scale model of the solar system, the Earth's path around the sun would look like a circle. So would Venus. Mercury, you might be able to tell. Mars, you could tell, is elliptical. Mars is the most eccentric. It's a good thing that Kepler chose to examine the path of Mars through the sky, because if you had picked one of the other planets, you wouldn't have come up with the ellipse, because the data wasn't precise enough. But for Mars, yeah, you could tell it was an ellipse. Second law. Well, this one kind of makes sense. Let me redraw an elliptical orbit here. So here's the sun, and here's my spacecraft way out here. Now, here's what I want you to look. You see that it's moving like this, but as it gets closer, what happens to the force of gravity as it gets closer to the sun? It increases, right? So as gravity comes in, it's going to increase, and it's going to fall faster, 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 and then as it goes away, as it's moving away, what does gravity do? It slows it down slower, 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 slowest, a little faster, a little faster, a little faster, a little faster, a lot faster, a lot faster, a lot faster, slower, slower, slower. So it kind of goes like this. Slow, slow. Like the sound effects? All right. So I don't think planets actually make a swishy sound in space, but yeah. The swishy sound will be on the... Now, here's what he derived empirically. Now, if you take AP Physics C, next year, you juniors, or you take a calculus-based physics class, we'll actually derive this, but for this class we're just going to state it as empirically true, because that's what Kepler did. He just noticed that it was true. If you take out, like, if you wait a month, let's say this is an asteroid or a comet, if you wait a month, in 1 month the asteroid might move from here to here. And so it's going to sweep out a little area, a little wedge shape. And we take the area of that. Well, as this thing goes faster, in equal times it's sweeping out more area. So that if you look at it when it's moving really close, it's moving really fast. So it's going to go swoosh like this. It's going to sweep out that much area. Now, if this was going from here to here, if that's 1 month, and going from here over to here is 1 month, these two areas are the same. So the way we state that is planets sweep out equal areas in equal times. Now, Kepler did not know why, but since then we've discovered this quantity called angular momentum and torque and so on. We're going to talk a little bit about that later in the year. And the fact is that the angular momentum is conserved. And so, and when angular momentum is conserved, these areas, you sweep out equal areas in equal times. But he didn't know that. You don't need to know that for right now. Just know that this is what Kepler noticed. That's the second law. Now the third law, he derived empirically, but we're going to prove it for circular orbits. What he said is this. Whoops. The period of the orbit squared is proportional to A, the semi-major axis cubed. These two things are proportional. This is not an equal sign. It's a proportional sign. Another way of saying this is that A cubed over T squared equals a constant. He noticed this, that if you take, now what is A? Let's take a look at this. They showed it in the video we watched, but A is the semi-major axis. It's the distance from the center of the ellipse to its maximum distance away. That's the semi-major axis distance. So this is A from here over to here. A cubed over T squared is a constant for no matter what planet, as long as you're orbiting the sun. This is going to be true for an elliptical orbit. And I'll show you a little table that shows that this to be true for the sun and all the planets in our solar system. But he derived this empirically, and this took him, years. We're going to do it in 5 minutes or less. Because we have Newton's law of gravity. So imagine here's the sun. Mr. Sun. I think the sun wears sunglasses. All right. And here's a planet in a circular orbit, which I'm going to draw kind of in perspective here. It's moving around like this. So this has mass m. This is our planet, little m. And we know that the force of gravity is equal to the gravitational constant times the mass of the sun times the mass of our satellite, our planet, over r squared. Now that's from the center of, r is from the center out here. Now, this is the radius of our orbit. Well, if you take an ellipse and squish it into a circle, the A turns into an R, right? The semi-major axis is just the radius of the circle. But we also know that if this is moving in a circular, this force is a centripetal force. And it was Newton who came up with that. So this is the mass of my object that's moving in a circle. Here's the force on it, that force of gravity. So that's going to be equal to mv squared over r. So the force of gravity is a centripetal force. But we also know that since our planet is moving in a circle, that the speed of the planet is equal to the circumference of a circle divided by the time it takes to go around once, which we call the period of the orbit. So now I can take this and plop it in here. So we're going to do that. So GMM over r squared is equal to m over r, that's from here, put that right here, times v squared. Well, I'm just going to square this, and I get 4 pi squared r squared over the period squared. Well, this is really messy, so let's clean it up. What cancels out on both sides? The mass. What cancels out over here on the right side? The r cancels with the r squared. Now I'm going to rewrite it one more time. Gm over r squared equals 4 pi squared r over the period squared. Now, do you remember how to cross multiply and divide? Well, this is in terms of the period squared, so let's solve for the period squared. The period squared is equal to this times this divided by that. You remember that from 6th grade math, I think? You're doing fractions and stuff. Cross multiply and then divide by that to solve for this. So you get 4 pi squared, and what is r squared times r? R cubed. Over, now divide by this. And we've done it. This is Kepler's, this is Newton's version of Kepler's third law for circular orbits. Now when you get to a more advanced physics class, if some of you decide to study physics, you will actually do the proof for elliptical orbits, but that's beyond the scope of this class. And I don't remember how to do it, quite honestly. But look, let's look at, if I go r cubed over t squared, I get a constant. Now, what is that constant? Well, it depends on what units you use, and so on. But if you look in your book, here's our book. It's on page 125. Okay, this is table 5.2. And so here we have the 9 planets. This book still includes Pluto. By the way, Pluto doesn't care if it's a planet or not. It's just it's an inanimate object that's very, very far. And there is a reason to call it something other than a planet. I think they should have called it, well, they call it a dwarf planet. I think they should just call it a minor planet. It's big enough to pull itself into a sphere, so it's not like a small asteroid or planet. You know, it doesn't orbit another planet, so it's not a moon. But it's not like one of the big planets, like Venus or Mars or Earth or whatever. So calling it a dwarf planet is fine with me. But look, here's the average distance from the sun. And they called it S for some reason. We were calling it R. And here's the period in Earth years. Now they're using years, not seconds. So the units are a little goofy here. But if you go the radius cubed over the period squared for all the known planets, you take this ratio, look at this number. It's the same, or pretty much the same. Close enough. So this is a really amazing thing that Kepler discovered. Kepler's one of the first people to look at the sky and find mathematical, mechanical patterns in the way the planets are moving. And he was trying to bring order. Now, as they said in the video, he had this construction of the 5 perfect solids and all of that, and he thought the spacing was based on those solids, and that turned out to be completely wrong. But still, he was able to, find something really profound in the way the planets move around the sun. And that was laid the foundation for an even more amazing human being, Isaac Newton, to make further discoveries. And we're still making discoveries today, people. I mean, in my lifetime, I'm what, 55 right now? In my lifetime, we've discovered 96% of the universe that we didn't know about. Turns out the stuff that we're made out of, atoms, protons, neutrons, and electrons, is only about 4% of what the universe is made out of. There's this stuff called, they call it dark matter and dark energy. They call it dark matter because there's matter that suffuses the universe that doesn't interact with photons. And since we're electrical beings that deal with photons, we can't detect them, but we can see their gravity. So most of the universe has been discovered in the last few decades. In your lifetime, we've discovered gravity waves for the first time. We're detecting gravity waves. When 2 black holes or 2 neutron stars collide, they send ripples through time and space. So there's a whole lot more to be discovered. But Kepler was one of the first, if not the first, great astronomical physicist. And so, good for him. Well done, Kepler. So, the 3 laws, elliptical orbits. Let me zoom out so you can see the whole thing. Come on. Yeah. Elliptical orbits with the sun at 1 foci. You move faster the closer you are, such that you sweep out these little wedges that you sweep out. The area of these wedges is the same for equal time periods. And that the period squared is directly proportional to the radius cubed. And so that's on one sheet of paper is a lifetime of work. It's pretty amazing. Okay. That is all.